In the previous section, we learned that if we have products and quotients, we can't just take the derivative of one piece at a time. In the previous section, we actually did that operation. But there's going to be times where it's going to be difficult, or you're not going to want to multiply or divide things out. And in those cases, we have product rules and quotient rules to help us find derivatives. So I have written down the product rule. Written out in function notation. I'm going to write it in a slightly simpler form so that it's a little bit easier to memorize. So if your function is a product of u times v, then the derivative of that product is the derivative of the first times the second plus the derivative of the second times the first. So u prime times v plus v prime times u. Let's see how this works in a couple of examples. So in my first example, f of x equals x to the third plus 2x squared. This is the same thing as x to the third plus 2x times itself. So that means both my u and v are the x to the third plus 2x. Then my u prime would be 3x squared plus 2, and the v prime should be the exact same thing. Plugging this into my product rule, I'm going to take u prime, which is 3x squared plus 2 times v, x cubed plus 2x, plus v prime, 3x squared plus 2 times u, x cubed plus 2x. You've got a couple options for simplifying. You could FOIL all this out, combine like terms, or because in this special case, these two expressions are the exact same thing, you can actually add them together. And you can say that f prime of x is 3x squared plus 2, x cubed plus 2x. Example B, this time I'm going to say the u is square root of x, which is the same thing as x to the 1/2. And my v is 3x minus 4. U prime would be 1/2 x to the negative 1/2. And v prime is just 3. Plugging this into my product rule, I'm going to take u prime times v plus v prime times u. I think to simplify this, I am going to distribute, get rid of parentheses, and combine like terms. 1/2 x to the negative 1/2 times 3x. Let's see, 1/2 times 3 is 3/2. And x to the negative 1/2 times x to the 1, if we add the exponents, is x to the 1/2. 1/2 x to the negative 1/2 times negative 4 would be negative 2 x to the negative 1/2 plus 3 x to the 1/2. And then I've got some like terms. I can add those x to the 1/2s together. 3/2 plus 3 is 9/2. So I get 9/2 x to the 1/2 minus, and I'm going to write this second term as a 2 over x to the 1/2. This answer is great. You can leave it like this. Or if you want to write this using radicals, you could write this as 9 square root of x over 2 minus 2 over square root of x. We also have a quotient rule. I'm going to rewrite the quotient rule without the function notation, again, just to make it a little bit easier to memorize. So if f is a quotient, u divided by v, then the derivative would be u prime times v minus v prime times u all over v squared, where u is the top, v is the denominator. So let's see how this works with some examples. In example 2a, my u would be 3x minus 2, and my v is x plus 1. So u prime is 3, and v prime is 1. Plugging that into my formula, I take the u prime times v minus v prime times u. and then all over v squared. To simplify, I would get rid of parentheses and combine like terms in the numerator. So if I distribute, I notice that when I combine like terms, I can cancel out the 3x's. And let's see, 3 plus 2 is 5. So my final answer would be 5 over x plus 1 squared. Here's another quotient. And example 2b, my u, my numerator, is now 3x minus 2 times x squared plus 1. My numerator is actually a product. And my denominator is 2x minus 4. You've got some options here to find the derivative. If you want to FOIL out the numerator, you can definitely do that. You can multiply those things out and then find the derivative. Or you can use the product rule. I am going to use the product rule because I want to show you that you can use a combination of these rules together. So over to the side, I am just going to think about 3x minus 2 times x squared plus 1. My u is the 3x minus 2. My v is now the x squared plus 1. U prime would be 3, and v prime is 2x. Using the product rule, I take u prime times v plus v prime times u. This is my u prime. This is the derivative of that product. I would probably distribute and combine like terms. And so if I distribute and then combine like terms, I get 9x squared minus 4x plus 3. So that's the derivative of my numerator. And then back to my quotient, the denominator was 2x minus 4, and the derivative of that is 2. So plugging this into my quotient rule, we take u prime times v, so 9x squared minus 4x plus 3 times 2x minus 4, and then we subtract v prime times u, and all of this is over v squared. Now in terms of simplifying something like this, you could definitely distribute, do lots of multiplication, combine like terms. That's about all you can do. On your exams, which are going to be timed and in the testing center, I'm going to be okay if you just leave your answer like this. I don't want you to waste your time doing lots of multiplying. But there are going to be some homework problems where they're going to require you to do all this multiplying. And so I'll just do the multiplying pretty quickly. So I distributed the 2x and then the minus 4 to everything in parentheses for that first expression. I FOIL out the second expression, and then I'll distribute the negative 2. And I just noticed I had a little mistake here. This should be an 18x to the third. I combined like terms and then distributed that negative 2 at the end there. If I combine even more like terms, this is what I have in my numerator. And my denominator is still 2x minus 4 squared. I did that pretty quickly. Hopefully I didn't make any mistakes. If I did, feel free to shoot me an email. And so that would be my solution. Again, on an exam where you're kind of timed, I don't want you to waste your time multiplying, and this first answer would be perfectly fine. But I did want to show you that you can multiply things out, and you might be asked to do that in some of the homework. So finally, I want to show you how we can use these product and quotient rules to solve problems with tables of values. This would work with graphs as well when we don't have equations. So basically in this table, they are asking us to find the derivative of a product and then the derivative of a quotient. For our product, they're saying that the u is function f and the v is function g. So at x equal 1, my u would be that value 2, and my g is that value 4. I just read those numbers right off the table. I can get my u prime and my v prime from that table as well. U prime would be the f prime, or negative 2. V prime is g prime, or 5. Again, just reading those numbers off the table. And now it's just a matter of plugging these into our formulas. So to find the derivative of a product, I take u prime times v plus v prime times u. So in this case, that's negative 2 times 4 plus 5 times 2, or negative 8 plus 10, or 2. So the derivative of that product would be 2. The quotient rule says we take u prime times v minus v prime times u all over v squared, plugging those numbers in. That's negative 2 times 4 minus 5 times 2 all over 4 squared, or minus 8 minus 10 over 16. That's negative 18 over 16, or that reduces to negative 9/8. All right, let's do one example of an application, as you are going to continue to see applications in all of our future sections. So this problem gives us a cost function. This is the cost of producing X televisions. We are asked to find the marginal average cost. That word marginal is telling me to find the derivative, and that word average is actually telling me I have to write a function for average cost. To find an average, you always divide by the number of items, or in this case, you divide by X. So the average cost here, which our book denotes as C bar, is going to be C divided by X. Or in other words, we take this cost function and then we divide it by X. Dividing by X is the same thing as multiplying by 1 over X. And so that gives me 10x plus 50 divided by x squared plus 2x. So what I have right now is an equation for average cost. To finish this problem, to find the marginal average cost, I have to take the derivative of that function. Because I have a quotient, I have to use the quotient rule. My u is the numerator, and my v is the denominator. So that means my u prime is 10, and my v prime is 2x plus 2. Plugging that into my quotient rule, I take u prime times v minus v prime times u, and all of that is over v squared. We could do some simplifying by distributing, getting rid of parentheses. So I FOILed out I guess it's the v prime and the u. I distributed the 10, and then finally I'm going to combine like terms. 10x squared minus 20x squared is minus 10x squared. 20x minus 100x minus 20x, I need to change this, should be a minus 100x. And then I have a minus 100. All of this over that denominator squared. Finally, in this problem, they want to know what is the marginal average cost when x is 50. So that means we're going to have to plug 50 into this function. And now this is something that I'm going to need a calculator to finish. So I put this into a calculator. There's my solution at the bottom of the screen. So I put this into a calculator, and there's my solution. Looks like negative 0.0044. Why don't we round, I guess, to 4 places after the decimal? So we said this was negative 0.0044. Then this would be dollars per item. So the average cost is going to be going down just slightly when you produce additional items. That's it for this lesson. As always, let me know if you have any questions.